All right, so our test is tomorrow. So today we're just going to be focusing on the checklist we ended yesterday with and just going through it, making sure we're all clear on what to expect. So the first thing I said is for this first bullet point, be able to determine graphical characteristics of functions using calculus strategies. So anything that I put as a bullet point here, local and absolute extrema, increasing, decreasing intervals, concavity intervals, points of inflection. Okay, any of those you should be able to do for a given function. So I'm about to make up a function that we're going to work through. On the test, expect different functions to be provided for each of these questions, for each of those bullet points. But I'm going to just pick one function and do everything to it just to kind of save some time. Just give me a second to come up with a function. I'm just going to press pause here so there's not a complete bunch of dead air here. So let's pause this for a second. Okay, guys. Okay. We're going to be given f at x equals x to the 4 minus 20x cubed plus 72x squared plus 10. Okay. Determine. Okay. So A, we're going to say local and absolute extrema on the interval. I don't remember what I did here. We're going to go on the interval -2 to 6.
So you could give with or without interval on the test?
Right. So we'll go through what to do if there's no interval, but let's say if it is an interval for now. Okay. So, okay, this question's on the test. What are you going to do? Find derivative. Good starting. Okay. So first derivative, f prime at x is 4x cubed minus 60x squared plus 144x plus 0, right? Okay, so derivative found. How do I use the derivative to help find extrema? Let f prime at x be 0. So I'm letting f prime at x be 0. What do you notice you can do for the right side here? You can take out 4x. Yes? Take out 4x. What's left if you take out 4x? X squared minus 15x, 144 divided by 4, 36. Okay. There's the factored out 4. Okay. Okay, so what do you think? So you have you've done GCF, you have a quadratic left in the brackets. You should confirm to see if you can factor it. Is this a factorable quadratic? Are there two numbers that sum to -15 and multiply to 36? 312, or -3, -12 more specifically. So we got x equals 0, 3, 12. So you have just discovered the 3 values that cause the derivative to be 0 here. Okay. Now, are all of those, this is what you should check, because you're going to go off on a literal tangent here if you do this. When you look at those numbers, because it's on an interval, are all of those numbers valid? So even though those 3 totally all give you horizontal tangents, or that you're going to potentially change from increasing to decreasing, or slash, you're going to have mins or maxes at all 3 of those places potentially. We only care from -2 to 6, so 12 is extraneous.
So if it was no interval,
then you'd have to keep it in.
Okay.
Exactly. Okay. So we'll go through the process as if it's the question asked. If there was no interval, 12 would stay. So now what would be your next step? So you've got these two numbers. So when you have an interval, guys, do you get that no other locations could potentially be your min or max except these two and the endpoints. So this would be a case where you don't necessarily have to do an increasing, decreasing chart to confirm mins or maxes here. You just need to confirm what's the biggest value, smallest value at 0, 3, -2, and 6. Is this making sense? So I'm just gonna find f at -2, f at 0, f at 6, f at 3, and f at 6.
So when would you use the?
If it was no interval, then if there's no interval, then you kind of need a visual of increasing, decreasing to confirm the mins, maxes. Okay? Okay, so now it's number crunch time. I have to put these numbers back into the original. So remember the shortcut I said, if you want, you can store -2 in and then just use answer to the 4 if you want. These numbers aren't that horrible that you could do it. You don't have to do that. So -2 to the 4, 16. -2 all cubed is -8 times -20. So I think we got 176 so far. -2 squared is 4 plus 4 times 72. And then plus 10. So I'm getting 474. You guys can help confirm me here. 16 minus 20 times -2 cubed plus 72 times -2 squared plus 10. So I did it two ways. I got 474. Zero's nice. Once you put 0 in, you get 10. You put 3 in, 3 to the 4. Okay, minus 20 times 3 cubed plus 72 times 3 squared plus 10. So I got 199. And then for 6, 6 to the 4 minus 20 times 6 cubed plus 72 times 6 squared plus 10. I just got -422. Okay. Can we now classify each of these as local or absolute min or max? It's literally just compare the numbers, right? You're just saying, do you guys get any other number other than these 4? Every other number, the graph's either on its way up or on its way down. So no other place could have a min or max. These are the only places. So now just classify them. You look there. What's the biggest of all the numbers? So this is going to be your absolute max. So it also will be a local max. Okay. You don't have to say local and absolute. If you say absolute, it's understood. It's also a local. Okay. And then I look at the numbers, and can you obviously tell the absolute min? Negative, then only -1, -422. So there's my absolute min. So for this one, because it's on an interval, life is a little easier. The only trick was you had to remember to remove 12 from the equation, literally. Okay, because it's not a solution. And you just now have to identify what's happening at the other places. So, and it's helpful, guys, to do it in order, because now if it goes from a max, what should happen next flowing from this function? If it's max, it should go, if this is a max, the graph's heading downward to 10, then upward to 199, then down to this. So you guys get this is going to be local min, and then another local max. So now just don't just leave it like this. I don't mind if you write this next to it, but I would like you to have some conclusion. So you're going to say, therefore, absolute max of 474 at x equals -2. Local min of 10 at x equals 0. Local max of 199 at x equals 3. Absolute min of -422 at x equals 6. Answer. Everyone good? That's how you answer it if it's on an interval. Because as soon as it's on an interval, you're guaranteed there's an absolute max and a min, and then the other two just have to, that's why you have to kind of go with the flow here. Now, if you wanted to, and you're like, I want to confirm with my sign chart, go right ahead. You can make a little increasing, decreasing chart to confirm everything. Okay? Now, if there was no interval, right? If there was no interval, you guys get everything would be the same up to here, but 12 would stay in the mix, right? 12 would still be there. And then you kind of need to do either one of two things. You can either do second derivative test or an increasing decreasing chart, i.e. the first derivative test, to confirm the max and mins. Yes? But the only places that could potentially be maxes and mins would be 0, 3, and 12, because there's no other places that potentially are your max and min. Because now, as soon as it's not on an interval, you got arrows at the end, and so now you're not guaranteed absolute max or min anymore. There still might be one. Because it's a quartic, will there be some absolute something here? Think of your graph of a quartic. There's going to be an absolute min, but there's not going to be any absolute maxes because the graph keeps going up, 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 up. Fair enough? So, you guys want to repeat the process if there was no interval? Just so you have it. So if you did it with no interval, so if it was just the local and absolute extrema, but I don't give you an interval, I'm just going to say the f prime at x part, all that part would be the same, right? Maybe I'll just do this. So if you guys get, I'm just going to do dot, dot, dot. So I do the exact same process that I did in the first one. All of these first 4 lines would be the same. I would have x equals 0, 3, 12. I keep them all this time though. Okay? And now I have them all. Shall we just go with first derivative test? i.e. increasing, decreasing chart?
Yep.
So if I do that, I have negative infinity to 0, 0 to 3, 3 to 12, 12 to infinity. I have f prime at x and f at x. Okay. So I choose my test values. So again, maybe I'll just copy the function here. 4x, x minus 3. So the derivative was 4x, x minus 3, x minus 12. The ones we put a negative number in there, guys. Negative number is going to be overall sign. Negative number times 4, like negative 2. Negative 2 times 4 is a negative number. Negative 2 minus 3 is a negative number. Negative 2 minus 12 is a negative number. Negative times negative is. So my graph is decreasing. 0 to 3. Okay, pick a number in there. 1. 4 times 1 positive. 1 minus 3 negative. 1 minus 12 negative. Positive times negative is positive, increasing. 3 to 12, I pick 5. 4 times 5 positive. 5 minus 3 positive. 5 minus 12 negative. Overall, decreasing. Bigger than 12, 15. Well, 4 times 15 positive. 15 minus 3 positive. 15 minus 12 positive. Positive. Okay? And again, one thing we could have done here that you still need to do is at 0, 3, and 12, you do need the y values. So I would have probably just done that here while I got those 3 numbers. We know we got 10 for this one. For 3 we got the 199, right?
Yeah.
And then 12 we never had to find, so now I have to find the 12 just to have it as a comparison number. Do you kind of get that's going to be a really big negative number? Yes? So let's find it. So negative bracket negative 12 raised to the 4 minus 20 times negative 12 raised to the 3 plus 72 times negative 12 raised to the 2 plus 10. I just got, no,
You just find negative.
because I don't know what I'm talking about. 12.
Okay.
Okay. 12. 12. I think I decided in my head it's going to be a big negative number, so I decided I'm just going to make it negative. So no, 12. Because I got like 65,000 my calculator, and I already went, that makes no sense. So okay, 12. 12 to the 4 minus 20 times 12 to the 3 plus 72 times 12 squared plus 10. This is better. I got negative 3,446. Okay? As people laugh at me. Ah, that's a number. Don't diss negative 3,446. What's ever done to me? Big guy. Okay. You guys get that half of the polynomials. The numbers can get big, so don't be shocked tomorrow. The numbers are in the hundreds. Okay, in the thousands. Okay. So there it is. Those are the 3. We just have to classify what's happening at those 3 places. Does this chart help you do that? And can you obviously say, so again, if the graph decreases, then increases, then decreases, then increases, okay? right? And again, draw, decreases, increases, like you guys get, there's your W, with the exception that one of these dips is at 199 and one of the dips is at negative 3,446. So it's more like that shape, right? So if that's, having that little picture to kind of just go with it, do we obviously see there is an absolute min, okay? But then there's a local min and a local max. So those are going to be the three things you're going to say, okay? So the sign chart here, though, only tells you local, okay? It tells you local, and then you have to compare numbers to confirm it's absolute. So this is the way I would say it. Let's go in order. So since f prime at x changes from negative to positive at x equals 0. Therefore, f at x has, it's from negative to positive, guys, local min of 10. Right, that's wrong. 10, 199, that's what it should be. 10, 199, negative. Okay, of 10 at x equals 0. Local min of 10. Okay. I don't need to write anything more than that because it's not also absolute, right? There's another min that's going to be a lot bigger. So I'm just going to leave that. Two more since therefore. Since f prime at x changes, well, I'm going to do it separately. From positive to negative at x equals 3, therefore f at x has a local max of 199 at x equals 3. And then the last statement, since f prime at x changes from negative to positive at x equals 12, therefore f at x has, I'm going to say, a local min of negative 346 at x equals 12. But before I just continue on to the next question, what do you think I'm going to write? This is also the location of the absolute min. Yeah? This is also the location of the absolute min. If you want a justification, you could say negative 3,446 is less than 10. That's the decision making. That's what's made that absolute, because of the two mins, it's the smaller one. Okay, fair enough? Yeah, looking for the bigger one. Yeah. Okay. So, just keep your fingers crossed for an interval, guys.
There's just like, I feel like more rooms to make errors and there's no interval.
But you got to realize that sometimes they won't be one, right?
Yeah.
But I think if you guys get, if it's not the min max question, if it's just increasing, decreasing, or concavity, then who cares if there's interval or not,
Yeah.
really, right? Because you only care about, you need to make a sign chart anyway, right? Okay, so let's move on to a C. So what if I asked you same function, but I just want to know when is the function increasing and decreasing? Have you actually already done the work for that one already? By finding the extreme values, have you already done the work for that? You'd have to basically take this chart and reproduce it, right? So if the question was determine increasing and decreasing intervals, okay, I'm gonna cheat. Copy. Okay. So, look, it's dancing. Okay, sorry. Okay. So do you get that you would have to still, if this was, you guys get this part C, what if this was part A? Was this just the start of the question? Oh, I have to take the derivatives, A equals 0, solve for x, find the zeros. Like you guys get, like all of that part would have to be reproduced here as well. Okay? So you do So everything up to x equals 0, 3, 12, all of that would be part of the solution to this question. But now, the only thing that's different here is what you care about stating. In the last one, it was extrema. Now I care about the increasing, decreasing intervals. So you guys you can get away with doing this in just two statements, two since therefores, right? So let's remember how we do this. Since f prime at x is positive, so the way we can say positive is, you can say is positive or greater than 0, right? Is greater than 0 on what intervals? 0 to 3 and 12 to infinity. Okay. Therefore, f at x is increasing. You're all going to remember this on, what's the rule about increasing intervals? Include the endpoints if they exist. So what do 0, 3, 12 are the legit values. So on 0 to 3 and from 12 to infinity. Okay? Since f prime at x is less than 0 on negative infinity to 0 and 3 to 12, therefore f at x is decreasing on negative infinity to 0 included and 3 to 12 included. That'll be the end of that question. Okay? Everyone good? Okay? That's how you do increasing, decreasing. Okay, what if I asked you to determine the concavity? Okay? When f at x is, it'll say determine concavity intervals. Okay, so this time, again, remember, it might just be here's f at x, determine concavity of the intervals of f at x. So what would you need to do? What would be the first step? You'd need the second derivative. But before you can find the second derivative, you need the first derivative. 4x cubed. What was it, guys? 4x cubed minus 60x squared minus 60x squared plus 144x, right? So take let's take the derivative of this. So what we got 12x squared minus plus, okay. And then what should I do with this? I should let f double prime of x equal 0. So what can I do here? I can take out, leaving me with x squared minus plus, okay. I meant for this to work, and I made a boo-boo somewhere. That's okay. It's still, even though it's not, you guys I look at that, you should try to factor it. Is this going to be factorable? All right, 12, 6 and 2, 4 and 3, nothing's happening with the 10. So, but it's not, just because it's not factorable, because you can still do solvable, because you can use quadratic formula. So, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. 100 minus 48. So 10 minus root 52 equals divided by 2 is 1.3, or let's just go with one decimal place, 1.4. And 10 plus root 52 equals divided by 2 is 8.6. There are the two locations. Could you then, so what do we do? So we found the two locations where the second derivative is 0. No, the interval O was only for part A, everything else is no interval. For concavity interval, okay, yeah, so that's not the second derivative. Second derivative test is to confirm min-maxes. Gotta be careful. The second, just using the sign chart for a second derivative. That's what we want to do, right? Because that's going to tell us concave up, concave down. So negative infinity to 1.4, 1.4 to 8.6, 8.6 to infinity. So pick a negative number. Pick a negative number and put it into here. So this one is a little, because it's not factorial, it's a little more annoying, but still doable. So if I pick a negative number here, let's pick a concrete number, -2. Sure. So if I put -2 in here, -2 squared is 4. -10 times -2 will be +20. So 4 plus 20 is 24. 24 plus 12, 36. So positive times 12, positive. Positive means original function is concave up. Okay? And then from 1.4 to 8.6, pick 2. 2 squared 4. 10 times 2 is 20, but now it's 4 minus 20, so that's -16 plus 12. -4 times 12 negative. Concave down. And then bigger than 8.6, 1,000,000. Like, I mean, like it's going to be positive, right? Okay. So since f double prime of x is greater than 0 on negative infinity to 1.4 and 8.6 to infinity, therefore f double prime of x is, since therefore f at x is what? It's concave up on, remember the rule for concavity intervals. Keep them in a cave, okay, always round, okay? So negative infinity to 1.4 and 8.6 to infinity, okay? Since f double prime at x is less than 0 on 1.4 to 8.6, therefore f at x is concave down on 1.4 to 8.6. Concavity intervals. Okay? If I wanted points of inflection, you guys you'd have to have done all of this part. So maybe this will be like the part B of a question. Instead of having to do points of inflection and having to do all this all again, points of inflection kind of go part and parcel with a concavity chart, right? Because when do points of inflection occur? When the sign of second derivative changes. We have two sign changes, so we're going to have 2 points of inflection, right? So if part T was points of inflection, okay, again, all the work you had to do for concavity would do, okay, so hopefully it would already be there. Since f double prime of x, you can be a little more vague for points of inflection, you just say changes sign, okay? Changes sign at x equals 1.4 and 8.6. Therefore, f at x has points of inflection. Now don't lose a silly mark here. If I want a point of inflection, you better tell me a point of inflection, okay? I'm going to say of, and I want points, okay? So I need 1.4, 8.6. How do I get the y values, guys? Back to original, right? F at 1.4, F at 8.6. Again, they're going to be approximate. To really be accurate, you really should use the more decimal place version to really get a more accurate answer. But if you use 1.4 and 8.6, I'm going to give it to you. So if I put 1.4 back into the original, so 1.4 to the 4 minus 20 times 1.4 to the 3 plus 72 times 1.4 squared plus 10. I just got 100.1. I could do the, and then 8.6 to the 4 minus 20 times 8.6 to the 3 plus 72 times 8.6 squared plus 10 negative, ugh, this is a big one, negative 1,915.9. Does that kind of make sense, though, thinking about what your mins and maxes are? Remember, between 10 and 199, I need to have a change of concavity. Between 199 and negative 3,446, I need to have a change of concavity. It's around halfway, not halfway down, or you know what I mean? It's around halfway over and halfway down. Not exactly, but approximately. So there you go. That's answering all the questions related to pieces of a function. Okay, so there you go. Now, what if I asked, gave you a function here? Let's do a separate example. So if I say, given f at x equals, just to save us time, guys, I'm just going to do a quadratic. I know it's easy, but be prepared for this. This could be a cubic or something. Given f at x equals negative x squared plus 6x minus 8. Okay. Determine the local extrema by applying the second derivative test. So now I'm giving you a specific way I want you to do it. I want you to use the second derivative test.
Are you giving this?
One time, yeah. There will be one time on the test. If you go back to the checklist, okay, there will be one time where be able to apply the second derivative test to locate a local min or max.
Are you gonna like specify that you want the other version or just
No, I want you to at least use the second derivative test once on your
yeah,
test.
okay.
Okay. So how does that second derivative test work, guys, to confirm a min max? So you first need to find the first derivative, right? So first derivative of negative x squared plus 6x minus 8 would be negative 2x plus 6.
If we use the second derivative way on the first
Yeah.
question, that's fine.
Yeah. Again, if it's on an interval, though, you don't have to, right? You don't have to prove maxes and mins. You just have to look at the flow of the graph, like of the values. But for if there was no interval, 100%. Yeah. Okay. So f prime at x equals negative 2x plus 6. Again, you still need to figure out the potential locations of the min maxes. That part's not. You still need critical numbers. 0 equals negative 2x plus 6. Just easily solvable, guys. Answer is yes. 2x equals 6, x equals 3. Okay. So instead of going to a sign chart, the second derivative says I should do what next? The second derivative test tells me I should maybe find the second derivative. Okay. What is the second derivative here? Negative 2. That happens when you start with a quadratic. If you started with a cubic, this would be linear, right? Like it doesn't matter. So f prime x is negative 2. You should still, the whole point of this is you want to find what is the sign of the second derivative at your critical point. So what's happening at 3? Well, it's a little redundant here, but you really should still show me this. F double prime at 3 is still negative 2. What am I just, do you guys get, this goes from generic everywhere to specific here, so that's why I want to see this. Why, how can I put this and the fact that the derivative is 0 here and the second derivative is negative here, can I put that together to confirm if I have a local min or max? Because you guys get, this is telling me that the graph is doing what at 3, if the second derivative is negative. Concave down. So if my graph's concave down and I have a slope of 0, then that means I have a local max. Okay? So this is your justification for second derivative test. Since f prime at 3 equals 0, and f double prime at 3 is less than 0. Therefore, you don't have to do this by second derivative test. Okay, by the second derivative test, f at x has a local max. Oh, what didn't I do yet that I should do? Uh-oh, I didn't find it. Can I find it? Right? Oh, you can always, if you ever forget, you can always find it, right? F at 3, I put 3 into the original. 3 squared 9, so I have negative 9. 6 times 3, 18. Negative 9 plus 18 is...
No.
What? Okay, 9. 9 minus 8 is 1. Okay, okay, final answer 1. I just haven't gotten to the minus 8 part yet. I literally said negative 18 plus 9, or whatever, or 18 plus 9 is, and you said... So, wait. Yeah, that's right. So 1, are we all happy with 1? So local max of 1 at x equals 3. Okay, guys, on your assignments, for some of you, when I asked for the local max or min, you just told me the point. You guys remember that's not the way I like it. Okay, I don't like it like that. Okay.
Oh, funny.
So you have to state the max and where it occurs separate because it's just better. Okay, a max is not a point. Okay, it's the y coordinates, so split it up. Okay. Okay.
I always forget, but for the y and x-intercept, those aren't points either, are they?
You should really, okay, so again, I was pretty lenient because a lot of you wrote coordinates. Okay, you can, but like, you guys get an x-intercept, you just tell me the x-intercept's 2, I know it's 2, 0. You don't have to write 2, comma 0. I already know that the y coordinate's 0. So usually for intercepts, you just state the value. So if I say, what's the y-intercept, you just state 5. X-intercept, 2. You just write the number. And I don't even really like you writing x equals 5, y equals 2, because now it starts looking like asymptotes. Okay, so asymptotes have to be equations, but intercepts should just be the numbers. You don't need to write coordinates. Okay, so do you guys get what I've just spent a good chunk of time on is actually a good chunk of the mark of your test. It's the knowledge section. All of this is knowledge section. So then what's left? So
Simple rational function, list of characteristics.
Yeah. Right. So given a simple rational function, okay, so let's talk about that one. So given a simple rational function, determine asymptotic behavior and make a sketch. I'm telling you right now, this is the majority of your communication mark. It's literally just find asymptotes, find behavior, make a sketch. There's actually going to be no calculus related to that. Did you guys all get my lovely picture last night?
Yeah.
So be able to do that. It'll be an easy, it's not going to be a hard rational function. It's not going to be one that's going to do weird stuff. It'll be pretty straightforward. Yes.
So the expected to find like x-intercept, y-intercept.
Yeah. Intercepts you should find. Asymptotes you should find. Behavior near asymptotes 100% with limits for the vertical. Limit as x approaches 2 from the right. Limit as x approaches 2 from the left. Horizontal, I'm okay if you just go as x approaches infinity, y approaches number from, and you pick above or below. Like that's my expectation for stating the behavior near a horizontal asymptote. Right, you're putting, right, all of those things, guys, you're putting in test values, right? So just put in your test value. You don't have to show me the test value, I just need to see the statements. But that's what you're doing, right? Horizontal behavior, putting in 1,000 and negative 1,000. For vertical behavior, you're putting in a number really, really close to your vertical asymptote, a little bit higher, a little bit lower to get your numbers. Fair enough? Okay? Okay. Do we need to do an example of that? I think we're okay. It's literally, think of the first question from the assignment, but with no calculus. Like with no derivative taking. So, and again, if you have a bit of extra time, you know, feel free to like do the first derivative, confirm it's like, and say, oh, it's always decreasing. Did my graph always decrease, or does my graph always increase? Like you could do confirm a few other features based on that. Okay, but you don't have to. It's not going to be expected. Okay. Now, given a list of characteristics of a function, make a sketch. So we've been doing that periodically throughout this unit, where I just give you a list of characteristics. You have to draw something that matches. So if I tell you some info about where it's concave up or down, where it's increasing or decreasing, where there's slopes that are 0, I just give you a list of characteristics. You have to make a sketch that just matches. Yeah?
We won't be given a function and then we have to draw like a vertical.
No. It won't be like that. This one will be more, I give you a list and you have to make a sketch that fits every category of the list. So do you guys want us to do one of those? Okay.
And Miss, for any of those, did you want to domain for any of
For the what?
anything on that? Or did you want to like ask for domain for anything?
No, not really. But do you guys get like, I don't know, not really domain, not really symmetry, but the intercepts are useful because it helps you anchor your graph, right? That's what I would expect you to be able to find the intercepts for that.
Yeah, I just didn't know if you needed us to state that.
You know, if you want to write for yourself, you can, right? Okay, so let's do one of those. So if I tell you, okay, sketch function, I'll say a polynomial function that satisfies the following conditions. Okay, so I'm going to say f at 0 equals 2. F at negative 3, f prime at negative 3 equals 0. F prime at 4 equals 0. F prime of x is less than 0 or on yeah. Hopefully that makes sense. So I gave you that. I gave you those categories, these characteristics. Okay. And your goal is to. All you're going to get from me is an XY no scale. Some of you, please read my comments, guys. Some of you need to work on your scales. Some weird scales were showing up. Okay. So just be careful. Like you can't go 2, 8, you know, like you can't say like that's 2 and that's 8. You guys see what I'm saying? Like you're like going like there's interesting things happening. Okay. So I'm gonna do a horizontal scale here so that I can keep things in proportion. Oh. 2, 5. Okay. Okay. So, now let's just make it happen. 2, 4. Do you guys want me to give you a scale?
Yes.
Please.
I'll think about it. Okay. Okay, so there it is. Okay. So out of all the info there, what's the most concrete piece of information? Get your like automatic half a mark.
0 and 2.
0, 2, right? 0, 2 is a point on the function. Ta-da. That's the only, you guys get that's the only thing that might be the same for everybody's here in terms of the graph. Now, the general shape should be the same for everybody, but depending on how you decide to increase and decrease in things, Yours might be more like squish, more stretched. That could change, right? Nothing else is required to be the same here, okay? So what do you think should be the next thing you kind of take into consideration? The decreasing and increasing. So what does that go part and parcel with, the decreasing and increasing? Is there any other piece of information? Like what has to happen if you change from decreasing to increasing? Yeah, there's going to be a horizontal tangent there, right? So can you identify one place where you decrease and then increase? Well, there's really only one, right? But when's the function decreasing? Is there anything on there that tells you when the function's decreasing?
When X is less than
When what is? Okay, what are you looking? Okay, there's all these different categories. There's this told me point on function, point on f. Okay, what is the second thing telling you? Let's do some translations. What is this row telling you? Slope's 0, right? Horizontal, so slope of f 0. So derivative 0. So my graph needs to be flat there. Okay. What does f prime at x less than 0 mean? Decreasing. Do you see what I mean? You have to translate the calculus into what it really means, right? This means decreasing. What does f prime at x greater than 0 mean? Increasing. What does f double prime at x greater than 0 mean? Concave up. What does f double prime at x less than 0 mean? Concave down. So you guys get I've given you instructions on how to graph this. You just have to. So if you turn all the calculus into just read the green thing and say, okay, my function needs to decrease for x less than -3 and then increase for x greater than 3. Sorry, that should be a -3. That's probably throwing everybody off. Okay, that should be a negative. Okay. So decreases to -3, increases after that. Okay. And then concave up and concave down. So let's think about this. So I have to my function decreases to -3 and then has to start increasing, agreed? And it increases forevermore, right? So what do you think should happen? So where should I be thinking about putting my point for -3? Like up here, down here, what do you think? Needs to go, you guys get, putting it up here is going to be not very helpful, because look, if I have to go up from -3, I'm never going to hit this point. Right? So I have to definitely choose a point below. So shall we just go like maybe around here? Just randomly pick here. Everyone good? We're just going to randomly pick this. That's arbitrary. Okay? But now that I have this, can I now use the fact that I've made this choice? I know I have to decrease to decrease before -3. And what else is happening before -3? Reading. Like don't ignore the concavity. You can't do everything and then look at concavity last. You have to do everything kind of all together. So to the left of -3, I'm decreasing. So I'm going to take care of this, decreasing. But what else is happening left of -3? Concave up. So concave up and decreasing. Can we all draw concave up and decreasing? Smiling and decreasing. Okay. So do you guys get that? My graph needs to be smiling and decreasing, but I have to be horizontal by the time I get there. Is this making sense? Now, do you guys get the rest of the time I'm doing my graph is always going up, 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 and away. Up, up, up. Never going back down, right? Already dealt with the decreasing. This is done. Taken care of. Finito. Okay? For concave up, I've dealt with x less than -3. I've already done that part. But it's still concave up until when? It's concave up until 0. So do you guys get, I have to still be concave up all the way to 0. Hey, I happen to have a point to aim to there. Okay, that's cool. So my graph has to be concave up, still concave up until I get there. But then what now has to happen? I'm going to be between 0 and 4. I need to be concave down. Am I ever decreasing?
No.
Never decreasing anymore. Always going up. So I have to decrease and be concave up. And then when does my graph actually become? What's the next key feature? What do I have to make sure happens? You've already dealt with this. You've already dealt with this. Haven't dealt with this yet. At 4, there's a horizontal tangent. So I have to decrease. I have to concave down until I hit 4. Concave down until I hit 4. But then here's the catch. What happens after 4? I'm still increasing, right? Increasing from -3 to everywhere. So still increasing, but now what's changed? Back to being concave up. So that's what happens at the end here. Whoop. Okay, is this still a legit quartic that I've created here? It's allowed to be flat. You're allowed to not always have to, when the derivative is 0, you can just flatten and then keep going. It's legal. So that would be this would be the function that matches that, all of that categories. So you have to kind of, again, you can't just go, okay, I'm going to do this first and get rid of that part. It's kind of, so you have to look at the whole thing as, like, holistically. So this is where you might want to, on scrap paper, just kind of go, okay, I'm decreasing. Oh, I have to make sure I turn around here. Like, just have like a little bit of a rough sketch going, and then make when you feel good, then put it on here. Okay. Optimization. Okay. So I'll end by narrowing it down a little for you. Okay. 100% there will be a revenue question. 100% revenue question. Be able to optimize, maximize a revenue. Okay? So my suggestion is that question we did about the apartment building, be able to do that question. Okay? Remembering that in that question you have to think about restriction-wise, what's restricting that process, right? You have a building that perhaps has limited rooms, right? You can't charge negative rent, you know what I mean? Like, so just think about that sort of stuff to consider your interval. And then in terms of a second optimization question, there will only be 2. So one is revenue. The second one, it will have something to do with a 3D shape.
Will it be that like Norman window one?
That's a 2D, but no.
I'm sorry.
Yeah, it'll be a 3D shape. So you're either dealing with a box or a can. It'll be a box or a can. And I'm going to tell you, there could be money involved, there might not be money involved. Meaning it could be the cost of producing the can or the box, or it could just be minimize the amount of material. So both will be minimized. Minimizing cost or minimizing the material. And you get a choice of 1 out of 2. So there'll be 2 questions, you choose 1.
So you don't have to do both of them? You just
Correct.
know which one to do.
Correct.
For the second.
For the second.
Oh, for the second.
For this one, this is the only thinking question on the test, is this optimization question. So to give you a chance to make a choice, there will be 2 there, and you choose 1.
So we have to do the revenue one, and then there's
Right.
going to be 2 options for the
Correct.
box.
Correct. This test is still only 4-sided, so it didn't become this ginormous test, guys. It's still just a 4-sided test. Okay? You can do it. There's nothing tricky. I did not go off on a weird, like, haha, I'm going to choose some weird shape or anything. It's nothing, as long as you know the strategy. So we didn't get a chance to do an example of optimization today, but let's just talk about it. What are you going to do? It's an optimization question. Here's the one thing you have to recognize. You're not going to be given any model. You have to create it. I will, for the can, give you the formulas for surface area and volume of a regular can. Remember, a regular can, what does a regular can have? What are the sides or faces of a regular can? 2 circles and a rectangle. So keep that in mind, that's the formula I'm giving you. Box, I am not giving you a formula. Do we all know how to find areas of boxes? Surface area of box, volume of box. If it's square base, okay, volume of box. Length times width times height. Right? Volume of square base box. So first, how does a square base box change? Same times height. Okay? So that's the volume of square base. You really don't, so I basically can give you 1 of 2 questions, guys. I can give you a square base box, or I can give you the cutting the squares out scenario. Okay, both of those are fair game. Okay, for the volume of the box, okay, that's the volume. So how do you find the surface area of the square base box? So again, guys, it doesn't hurt. You can always draw one and just like visually look. There's my square base box. Top and bottom are 2 2x squared, so because top is x squared, bottom is x squared. What are all the sides? XH's, how many of them? 4XH. What if it's an open top box?
X squared.
Get rid of an x squared. Okay? What if it's an open can?
Get rid of the.
Get rid of a what? If it's an open, if there's an open can.
2 pi r. No.
Okay, the area, this is the formula for the surface area of a can. That's full can, 2 circles, yeah. That goes away if it's open can.
Which one?
But you guys remember, that's the for surface area. What if now money's involved? And I tell you how much things cost. Then you guys have to break these apart and multiply by the associated costs of each part. So that's how you deal with the cost if cost is involved. Everyone got it? Okay. So, guys, today I can stay after school till about 3:30. I have a lovely dentist appointment at 4, so I cannot stay beyond 3:30 today. Okay. But you're welcome to come after school if you have questions. And then as well as tomorrow, I'll be here probably around 7:45 if you have any last minute questions. But the test is happening tomorrow during period 2. And then we move on to trig again. Okay? So I'm just going to stop the video, guys. I hope that today's review kind of solidified things for everybody. And again, don't get too bogged down in the review in the textbook. If you can do these questions, the ones we just talked about today, that's the expectation of what you should do. I would do reading lesson questions and only use, you do the review, it's good for the review, but, you know, I think only do questions that will look like the questions we've done in class. Okay? Sorry, Tracy, just one second. Let me just stop the video.